going to be talking about floods, droughts, tropical cyclones, fires, and then a little bit of sea level today. So some of the exciting headline grabbing things. So first, let's just look at floods and droughts. So obviously, floods and droughts are going to have a big impact on both people and natural systems. So here is a stark example of a flood. This is Houston after Hurricane Harvey. And so you can see, entire neighborhoods totally submerged, and you can imagine the damage, from a storm like this is in the billions of dollars, and entire suburbs of Houston looked like this. And so extremely damaging, extremely detrimental to society. And then droughts, our main concern with droughts, as we've experienced in California, has to do with agriculture mostly. So we, are still dependent globally, of course, on agriculture to feed ourselves as a species. So we either grow food directly and we use that to, it's processed and then we eat it in various forms, or we feed it to animals and we eat those. But either way, we have to grow our food. And so droughts are one of the major concerns of how climate change might directly impact human societies through its detrimental impact on crops. So floods and droughts get a lot of headlines and are very important in the climate change discussion. So what's going on with floods and droughts in terms of their relationship to global warming? So if we think back to our diagram, we're increasing greenhouse gases in the atmosphere, and so we're increasing the global average temperature. And so what does the increase in global average temperature do to the water cycle and thus influence floods and droughts? So first, what do I mean when I say water cycle? So water cycle, you, I'm sure, saw this at some point in your educational careers. We have evaporation, right? So that's just kind of the sun is giving energy to some open body of water. Those water molecules in the water are being broken apart by the sun's energy and float up into the air. There are gas in the air. So that's evaporation, changing from liquid water to gaseous water. And then you have the water vapor coming back together and forming liquid again in condensation. So clouds are not gaseous water, so they're not water vapor, they are liquid water. They're cloud droplets. They're forming little droplets that are large enough for us to see, which is why we can see clouds. So we can't see water vapor, but we can see liquid water, so we can see clouds. So we have evaporation of water, condensation of water into clouds. Eventually those water droplets get large enough so that they fall out of the cloud, so that the gravity that's acting on those water droplets is larger than some type of an updraft that's holding up the water. And so then they fall out. And when they fall out, we call that precipitation. And so then all the rivers of the world are just a process of this. You have precipitation somewhere on land, and then that water collects and flows back towards oceans. And then some of that goes through groundwater as well. So that's our water cycle. Evaporation, mostly from the ocean. So that's liquid to gas. And then condensation is gas, which we call water vapor, into liquid again. And then precipitation is just that liquid falling out of the clouds and then going back towards the ocean. So here's our base water cycle. And I'll just say this is kind of our starting point. So we'll say, okay, this is what it looks like in pre-industrial climate. And then we're imagining, okay, what happens as the water cycle, or what happens to the water cycle as the temperature increases? And Essentially what happens is the whole water cycle speeds up. So if we think about all of these, these paths in the water cycle, these are arrows, which means that they're flows, right? So they're representing the movement of water from one location to another, and they're representing it in terms of like a flow per unit time, which is what we're kind of almost always looking at in diagrams in science that have arrows attached to them. We call these vectors. And most of the time they have a per unit time in the denominator. So this arrow here would be, you know, some mass of water per unit time. And so in a warmed climate, all this speeds up, which means that you have more evaporation, more mass of water per unit time. And in this diagram, they split up. They have evaporation and then evapotranspiration, which just means that they're including also some evaporation that's coming from the pores of plants, but we won't get into that. Just think about evaporation increases in a warmed climate. And that just kind of like makes sense intuitively that you're going to have more energy incident on the surface, more radiation incident on the surface, which is mostly that long wave radiation coming back from the atmosphere, which we called back radiation in another lecture. So you have more energy hitting the surface, so you have more of those water molecules evaporating at any given time. And so then you're going to have more condensation, and you basically just accelerate all of this. So then you have more precipitation, and then more stream flow, and more flow of water back towards the ocean. So this, you know, you might, if you were to initially look at, say, some projection of precipitation going forward in the future, and it said, oh, precipitation is going to increase as it gets warmer. At first, that might not make perfect sense because it seems like, okay, where is this additional water coming from? But it makes sense when you think about the entire water cycle, that you can have increases in precipitation because you have increases in evaporation. You're not like creating or destroying water. There's no new water being created in the atmosphere or anything like that. It's just that the entire thing is moving faster, so you can get more precipitation at any given location. So let's look at actually how this precipitation increase is distributed in space, because it's not actually the case that all places get more precipitation as it's getting warmer. So some locations actually do see a decrease. And so this is what that looks like. So we have, this is global precipitation changes in the future. So this is from various projections from climate models, which are just computer models that are using our best understanding of physics to make these projections. So projected percent change, so we have this in percent, so this would be like 60% reduction, 60% increase. Percent change in precipitation in the year 2100 with a lot of greenhouse gas emissions over the next 80 years. And so 0 would be no change. And so all of the oranges and browns are decreases in precipitation, and the purples and darker purples are increases in precipitation. And so overall, you do have an increase in precipitation globally, but we do have a decrease in some locations. So Latin America, Mexico sees a decrease. Parts of Brazil, Amazon see a decrease. South Africa sees a decrease. Parts of Australia see a decrease, and the Mediterranean region sees a decrease. But then over a lot of the other land locations and over what we call the intertropical convergence zone in the Pacific, those show big increases in precipitation. And so precipitation isn't quite as straightforward as temperature, as you can see. So with temperature, as you increase greenhouse gases, basically gets warmer everywhere. And there's some distribution as to like it gets even warmer in the Arctic, and it gets even warmer over land, but basically it gets warmer everywhere. And precipitation is different. Precipitation is you get more precipitation overall, but some locations see a decrease, and some locations we expect to see an increase. And it's even slightly more complicated than that, because it depends on what season, what time of year as well, in terms of how you expect precipitation to change. So if we look at this, this is the graph for, or this is the map for precipitation averaged over the whole year. But if you break that up into different seasons, so winter, spring, summer, fall, you see that it actually depends on the season as well. So if we just look at, for example, in California, we are expecting to see in California a decrease in summer precipitation. And already, there's very little precipitation in the summer in California, but still we're expecting to see a decrease in that, a decrease in fall precipitation, a decrease in spring precipitation, but an increase in winter precipitation. So California is dry in the summer, we're expecting it to get drier, and then we're expecting for California the spring and fall to get drier, but then to have more precipitation in the middle of the winter when it's wet. So we won't go into all the locations on Earth and how the precipitation might change as a function of time of year in all these locations, but I think it's just important for you to know that precipitation is kind of complicated, and so it's kind of a case-by-case basis as to whether or not it will be rainier or less rainy at any given location. And it depends on the time of year, depends on the location. So if we go back to our map of total precipitation changes, and we think about, okay, California is kind of right on this border between, to the north, we're expecting precipitation to increase, and to the south, we're expecting precipitation to decrease. And in the middle, we're kind of at this no change of precipitation portion. And so does that mean that we actually will see no change whatsoever, or are there still important changes going on? Well, so it's important to consider that even if the average precipitation is not expected to change, or expected to change by just a small amount, the distribution of days with very heavy precipitation or days with very light precipitation, that might change. And so that might still have an impact on various things we care about. So when I say distribution, I'm talking about the same type of thing that we talked about last time, where you have some distribution of temperature, for example. That's what we talked about last time. We're going to talk about precipitation now. You have a distribution of temperature where you have some days that are very cold and some days that are very warm, but most days are in the middle. And so you're thinking about, like, how is this entire distribution changing as the climate gets warmer? So if we look at how this might change with precipitation, first of all, like, try to imagine what the baseline precipitation distribution would look like. So before, this is the same thing. It's like, how many days per year do you have a given amount of precipitation? So if you have 0 over here and some large amount of precipitation over here, what would the baseline look like? So it's not going to be like temperature, right? Like temperature, you had a situation where you had it wasn't very common to have very cold days, and then it gets more and more common in the middle. You have a bunch of days that are kind of near average, and then you have very few days that are very hot. But precipitation is fundamentally different, because you can't have negative precipitation, right? But you have a lot of days with 0. And actually, you have most days with 0 in most locations. So the kind of baseline pre-industrial climate looks something like this, where your number of days with 0 precipitation is actually where your peak in the distribution is, right? So most days have no precipitation. And then as you get more and more and more precipitation, like you have a really, really large amount of precipitation, that occurs very infrequently. So you don't usually have very many days with a lot of precipitation. So these distributions look fundamentally different than the kind of bell-shaped temperature distributions that you see. And so we can imagine, okay, what would the distribution do if you're just thinking about it getting rainier in general? So what that might look like would be that you would have less days with no precipitation, right? So if it's rainier, then your no precipitation days are less frequent. So this goes down here because this is the number of days with that amount of precipitation. So that goes down. And then at some point you cross over and then you have more days with this heavy amount of precipitation. So this would be just kind of the change in the distribution if it just got rainier in general. Less days without precipitation, that's this part. And then more days with very extreme, very large values of precipitation. That's that part. And then you could imagine it getting less rainy or drier. And so that would be this kind of other shift in the shape where you have more days with very little precipitation and then less days with large values of precipitation. So everything over here, you have a decrease in your frequency of days with these large precipitation values. And then you could have just a change like this. This would be the more extreme change, where you have a situation where you have more days with no precipitation, and then you have kind of less middle days, less days with moderate precipitation. So that's what this would be, this difference here. And then more days with extreme values of precipitation. So that's your kind of just more extreme case. And so similar to what we talked about before with temperature, I can ask you what you think might be the case on average over the globe in terms of what happens with global warming. Does it get just rainier in general? Does it get less rainy in general? Or does it get more extreme in general? So with the temperature one, we talked about how there's kind of a lot of hype around temperatures getting more extreme, and that you'll see a lot of headlines that kind of act like as the earth gets warmer, that we're expecting both warm extremes and cold extremes to increase and just everything to get crazier. But we showed that actually the data does not support that, and that in general, cold extremes are decreasing. We're seeing less very cold days, but warm extremes are increasing. So we kind of shut the door on that notion that temperatures just in general get more crazy. But for precipitation, this actually essentially is the case, that things do get just crazier in both directions. So over most land areas, we do expect temperature distributions to become more extreme. And what that means is that you have more days where it's dry. You have more days throughout the year with no precipitation. You have less days throughout the year where you have this moderate amount of precipitation. And you have more days throughout the year with extreme precipitation values. And you can imagine that that is not good for crops, for example, because like, you know, if you had a plant in your house and you said, okay, this plant needs 1 cup of water every week on average. And so normally I give it 1 cup of water every week. So that's 4 cups a month. And I say, okay, actually, I'm going to leave town for a month. If I just give it 4 cups today, then it should be fine. I'll come back in a month. like, so that's the same amount of water throughout the period, right? In each case, it's 4 cups divided by 1 month, same amount of water. But that's not going to be good for the plant because it needs that water distributed throughout time. And so this change in precipitation to get more extreme means that you're going to have, in a lot of cases, not an obvious change in the total amount of precipitation in some location, but you're going to have much more of it in short downpours or in fewer days, and then longer periods of time in between with no rain. And so that can be bad for crops. So looking at some actual projections of this, this is what we looked at previously with return periods. So remember, the concept of return period is this idea that some value, in this case of temperature, we're looking at how in a changed climate, it might go from some frequency, like once every 10 years, to once every year. So we would say something like a 1 in 10 year event for temperature in this changed climate is now a 1 in 1 year event. So something we used to see every decade is now something we see every year. And so with temperature, it kind of looked, it was this situation where the entire line just shifted up and to the left. And so I'll show you the same thing now for precipitation in these locations. And so precipitation, again, if it's more extreme, you kind of have this shift, but the whole line is tilted. This is this less days with moderate precipitation is what would be evident right in here, less days with moderate precipitation. But with the extreme values, it's very similar to temperature, where, you know, these very, very large precipitation events where you have big downpours and flooding type events, those increase in a warmed climate, so that you would get, you know, a once per century event would become a lot more in terms of the amount of precipitation you'd expect for such an event. Or you could say that a once per century event becomes a once per decade event, that type of thing. So that's our change in return period and our change in return value. And so that's just, again, to show you what this concept is. And then these are the actual maps. These are the actual projections of how these things change in the future. So this is daily precipitation 20-year return values per 1 degree Celsius of warming. So that means hanging out right in here. So this is 10 years, there's 100 years, so 20 years is somewhere in here. And we're looking at the change in the return value. So we're looking at, like, what's the change between this and this. And then the other map is the return period change. So here's our return value change, here's our return period change. So, and then this is in percent rather than like millimeters of rain. But we see that our 20-year return value change is, they're all positive basically over the land. So if we look at over the United States, we have something like 2.5 to 5%. So let's just call it 3% in here. So that means that our return values for 20-year precipitation events are increasing by 3% for every degree of global warming that we get. And so, yeah, the return values, I think, are less intuitive than the return periods. So this is the return period, again, is in years. So here's our return period in years. And so it's starting at the 20 years and it's saying, okay, what will that return period be in the future? So return period for present day 20-year return values of daily precipitation. So 20 is like our baseline right here. So that means that anything that's green is below 20. So it's saying, like, let's again take California in here. So it's blue. So this is 13, say, 13 or 14. Let's just say 13 right here. What that means is that what used to be a precipitation event that we would only expect to see every about 20 years on average, we will see it every 13 years on average for every degree of warming. So we've already seen 1 degree of warming. So that means that, yeah, a once per 20-year event is now a once per 13-year event. And then that would continue to decrease in the number of years between events as the temperature gets warmer. So the takeaway here for these maps is that almost everywhere you see an increase in the return value, and you see a decrease in the return period over the land. And so that means like almost all land locations are expecting to see an increase in extreme precipitation. So the more extreme the precipitation, the more you actually expect to see an increase in that. And that there's very few land locations, just kind of some parts of the Sahara Desert, basically, that we expect to see decreases in extreme precipitation events. So high level takeaway, over the land, we expect to see increases in very heavy precipitation days overall. This is one more way of showing that percent change in heavy precipitation per degree warming. So here's 0. Everything that's green and blue means increase. And so over the land, we expect to see increases in that almost everywhere. And this is actual observation. So all these other maps were projections going into the future. And then this is observations, percent of the contiguous United States, which just means the United States that does not include Alaska and Hawaii. So the lower 48 states, percent of contiguous United States with significant portion of total annual rainfall coming from extreme single day precipitation events. So this is just kind of another way to slice and dice the data that's saying the same thing. And that same thing is that we are seeing an increase in extreme precipitation events over time, in this case from 1961 through 2017. So more heavy downpour days. So one way to think about that would be to think of a calendar like this, where we have, say, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9 rainy days. And let's say each one of these rainy days rains the same amount of rain. And so this is, let's just hypothetically say July 1980. And then what we're kind of expecting in the future in a lot of locations is not necessarily a huge change in the total precipitation, but again, what I'm trying to emphasize is this change in the distribution, so that you can take these same 9 rainy days and now you are condensing them into the future. So now let's say this is July 2050. And so you have the same amount of total precipitation. In this case, it's still 9 rain clouds. But what I've done is I've just packed them into 3 days instead of 9 different days, right? So in this case, we have 9 days, and then in this case, we have 3 days. And so it's the same total amount of precipitation throughout the month, but it's all coming in shorter bursts in just in 3 days in this case. And so the difference between that is, you know, not any change in the total, but more rain when it rains, and then also more time in between rain events. And so that is, in general, not good for crops and for a lot of ecosystems. A lot of crops and ecosystems like rain more evenly distributed. They'd like a little bit every few days, not a ton, and then a dry period, and then a ton, and then a dry period, and then a ton. So that is a cause for concern. And so here's just one more projection of this type of thing, where this is putting together these ideas of very heavy precipitation when it rains, and then long periods of time without rain in between those heavy precipitation events. So the top is the precipitation change projection. This is the maximum 5-day precipitation change. And so what this is just saying is everything that's blue means that you're seeing an increase in your very heavy rain events. And then this is consecutive dry days, how many days you get without any precipitation and the change in that. And so everywhere where it's red, you're seeing an increase in the number of days where you have no precipitation. So it's just measuring this idea, or its projections in this idea that you have more rain when it rains and then more days of dryness in between those situations. And so like Mexico would be a really good example of this, where you have projected increases in extreme precipitation and projected increases in days without any precipitation. So one way to put this is that it does make sense to say that you can have increases in floods and droughts in the same location. So at first glance, that might seem weird. You might think, you know, what, like climate scientists are trying to have it both ways. Like you can't have an increase in floods and an increase in droughts in California. Like that doesn't make any sense. But this is saying, no, it does make sense. You can have an increase in floods and an increase in droughts at the same location because of global warming. And it's actually what we do expect. It's what all of the models project should happen. And it's basically because this whole water cycle accelerates. And so when it rains more. And then when it's dry, it's kind of dry more. And so floods and droughts can increase at the same time in the same location as far as climate change is concerned. So that was the precipitation part of this. It's also important to think about the evaporation part a little bit more when it comes to droughts. So putting some numbers on this, over most land locations, and this is important for fires as well, which I'll get to, over most land locations, we're expecting precipitation to increase, and that increases by about 2% per degree Celsius of warming. And we're also expecting evaporation to increase, or evapotranspiration, which just includes the water coming out of the pores of plants, the stomata of plants. So both of these increase, but what you might notice here is that the evaporation over land increases more than the precipitation over land. So what that is going to mean is that the land on average is going to dry out as it gets warmer. So even though you have more rain coming in from the top, if you have more evaporation leaving, and that increase is larger than the rain coming in from the top, then you're going to dry out the land. So since evaporation over land tends to increase more than precipitation over land, much of the land gets drier on average. And so this is a map of soil moisture changes. That's just a measure of how dry the land is. And this is a projection into the future. And so we see that over the United States, over the Mediterranean region, over South Africa, over Australia, over the Amazon, we're expecting to see decreases in soil moisture, largely because of evaporation increasing more than precipitation. So if we look back so this map, for example, is soil moisture. And if we look back at precipitation, so let's look, for example, look at China here. So we're expecting a decrease in a decrease in soil moisture in China. And if we look at our precipitation map, we see an increase in precipitation there. So that's interesting, right? Because that shows us that our decrease in soil moisture, our decrease in the amount of water in the land must be happening because there's an increase in evaporation that's larger than the increase in precipitation, right? It's the same, you know, concept of conservation of, before we've talked about energy mostly, but now we're talking about conservation of water. And so you have an input term and an output term. And so the input term for the land is precipitation, the output term is evaporation, and both can increase, but if evaporation increases more than precipitation, then you're going to have a net drying of the land. And so that's what we would be seeing in China in this case. And it is true also over a large portion of the United States, especially the, so anywhere north of this line where we're seeing an increase in precipitation. If we go back and look at our soil moisture, we see a decrease in soil moisture in a lot of those locations. And so that must be because evaporation is increasing more than precipitation. So this map is, again, important for thinking about agriculture and crops, and then also fires, because really, you know, what crops care about is not so much like how much precipitation there is, but it's how much net moisture is available to them. So if they're seeing a decrease in soil moisture, then that's going to be bad for crops. And so that's why we have the potential for a lot of decreases in yield in the future because of decreases in soil moisture, because of increases in evaporation as it gets warmer. So let's talk about, so that's floods and droughts. Okay, so let's do fires. So fires have been, fires have gotten a ton of headlines as well, especially in the last year. So there were fires in the Arctic that got a lot of headlines. There were fires, of course, in California over the past several years, the Camp Fire in particular, so Paradise, and then other high-profile fires in California. Fires in the Amazon last fall that were very headline-grabbing, and then fires in Australia over this last winter break. And I see a lot of the coverage tying it directly to climate change and to saying something to the effect of, you know, the world is on fire because of climate change, and, you know, this is like essentially like the most important, you know, iconic impact from climate change. So first, I think it's important to point out that wildfires are a natural part of the Earth system. So they're not like something that we haven't seen before. And in fact, they burn about 4% of the global land surface annually. So this is a map of where fires typically occur. And this is in grid boxes where you're basically saying like, okay, 100 would be 100% of this pixel tends to be burned annually. And it goes down to less than 1%. But anywhere where there's color at all shows where you do have fires typically. So that's one thing to just keep in mind, is that fires are natural. And so it's not a question of whether or not, like, I guess the right way to phrase the question is, are fires increasing because of global warming? Not just whether or not there are fires, because fires do occur naturally. And so then the other thing to keep in mind is that humans are going to be affecting fires in a lot of different ways. So first of all, humans ignite fires, both intentionally and unintentionally. So mostly intentionally, they ignite fires to clear land for agricultural purposes. So in a lot of locations, especially in the tropics and southern hemisphere, every year people burn land to clear it, and then they plant their crops there. So that's kind of the intentional part. And then sometimes those fires escape control and become wildfires. And then we have a lot of unintentional fires as well. So unintentional fires can be by accident, like for example, fireworks. And if you actually look at the number of fires in the United States, we see a huge spike around 4th of July. So humans unintentionally setting fires is a big part of wildfires, of course, which is why we have campaigns like Smokey the Bear, you know, only you can prevent forest fires. So wants you to put out campfires and things like that. But then very high profile unintentional fires in California have been due to PG&E transmission lines. So this is a map of these major electricity transmission lines in California. And so PG&E has been responsible for a lot of these major wildfires. Essentially, when you have like very strong wind events, whether it's very dry, they can blow down these power lines, and then the power lines start fires. And so that's another way that humans are affecting fires. So humans are, I'm trying to put the global warming effect into context with all these other potential influences. So humans are igniting fires intentionally and unintentionally. They're also totally changing the global land surface. So humans use a lot of the land, for example, for agriculture. And that actually ends up suppressing fires a lot. So if you change what used to be like a savanna grassland that kind of naturally has a lot of fires, you change that into crops that are kind of protected, and you might even use irrigation to put water on them, that's going to reduce fires by a great amount. And then humans also suppress fires once they're started, right? So we have firefighters. We have CAL FIRE in California that goes and sprays flame retardant on fires, and so are suppressing fires that way. And then, of course, there is this increase in greenhouse gases, which raises global temperature, and it dries out a lot of the land. So that's why it was important to talk about the water cycle first. So obviously, fuels being drier is more conducive to fires, and it being hotter, that's more conducive to fires as well. So increasing greenhouse gases does cause a situation where we would expect vegetation to be more flammable and fires to increase, but it's just one factor of a lot that's going on. So I made a diagram here of how people might affect fire activity through a bunch of different pathways. And so red would be that the human caused change in this variable is likely to increase global fire activity. Blue would be the human caused change in this variable is likely to decrease global fire activity. And then purple would be that we don't really know. So it's ambiguous whether or not the human caused change is going to increase or decrease fire activity. So ignition, we're increasing the number of fires that are started. So humans are definitely increasing fires through increasing ignition, like by fireworks. So that's an increase. Suppression, we're trying to put fires out. So that should decrease the total area burned. That pathway is that humans are decreasing total area burned. But this has actually an interesting effect. If we suppress fires and then we allow fuels or the vegetation to build up more and more and more, then we have a situation where when we do have a fire, there's a lot more fuel to burn. And so that can cause more intense fires. So that's kind of an unintended negative consequence of suppressing fires in a location for a long period of time, is that then when you do have a fire, it can be bigger than it would be otherwise because there's more fuel available for that fire to burn. People are changing the land use mostly from a wild situation to agriculture. And so that actually decreases fires. And then people are burning fossil fuels, which increases CO2 and increases global warming and increases drought or dryness, right? Decreases soil moisture. And so that should have a positive influence on fires, as in there should be more fires because of that. And so this is one pathway, but it's one of many. And so global warming also, in addition to changing, aridity, meaning dryness, or drought, it's also going to change precipitation. It's also going to change wind. It's also going to change ignition. And so these are less clear, those influences on fire activity. But the main one would just be that it's getting drier. Okay, so what's the total impact of all these things? Well, interestingly, considering all of the relevant activities that humans are engaged in with regard to fires, humans have caused a large decline in global fire activity. And so we've seen, ever since we've had satellites up measuring this very precisely, and that's since the early 2000s, we've seen a decrease in the size of fires, in the area burned, in the number of fires. And so overall, humans are decreasing fire activity on the globe. And this is a map of where fires have increased and where they've decreased. And so there are some locations that see increases in fire. But like, for example, if you look in Australia, where we had these recent fires that got a lot of attention, we've seen a decrease in fires there over the past 20 years overall. And in the United States, we are at some pixels here in California that have seen an increase. So it's kind of this situation where you have these, different influences forcing you in different directions. And the net effect is, in this case, a decrease in fires. So this is like just another way of saying this, like over time, human influence on fires, we have the increase in ignition, which should cause an increase in fires. We have fossil fuel burning, which should cause an increase in fires, but we have suppression of fires. We have people trying to put out fires, which should cause a decrease. And we have changes in land use, which should cause a decrease. And what's winning overall, the total, is we've seen fires decrease. So that's not to say that global warming doesn't have an effect on fires. It does. Increasing temperatures and drying the land should cause fires to be more intense and more frequent than they would be otherwise. But these other factors are outweighing that increase in temperature. And projections going forward show that should still be the case for quite a while. So they're projecting still decreases in fire activity over the long term, over the next 3 or 4 decades at least, due to these factors outweighing any increase in temperature or decrease in soil moisture or increase in dryness or aridity. So fires are kind of a complicated one also, and they're not really this straightforward, oh, we see this hockey stick in fires, and so that's this straightforward, iconic measure of global warming's impact on people. So I will end with one that is much more straightforward, and we'll actually come back to this in the next one, next lecture as well, and that's sea level. So sea level is not all that complicated. It's increasing because the ocean is warming up, and so the warmer water expands, and because ice on land, mostly Greenland and Antarctica, as well as alpine glaciers, that ice is melting and flowing into the ocean. And so that is because of increasing greenhouse gas levels. And so this is our historical estimate of sea level rise, and then our projections going through the year 2100. And so our kind of central estimate by 2100 is around 3/4 of a meter to a meter of sea level rise. So that's 3 feet by 2100. So again, that's not like Florida is completely underwater, but it's a problem for a lot of cities on the coast. But we can make this direct connection to global warming with sea level. And what does that mean in terms of like flooding events? So going back to this idea of return periods and return values, here is floods, but now we're thinking about floods instead of like from the perspective of just large rain events in some locations, from the perspective of the tide. It's like you have a high tide, and then that floods your city on the coast. And so here's our same diagram with return periods and return values, where we have in gray what's happened in the recent past, and then our return period. So this would be like a once per year flooding event, once per decade flooding event, and once per century flooding event. And then our change in that return period, and then our change in that return value in the future for various locations. And so let's just look at New York here. We are expecting, in the future, so this would be under a high emission scenario for New York, RCP 8.5, a once per century flood will be, it's not even on the chart, so we can't even do that one. So let's look at, RCP. So this is the lowest one, RCP 2.6. So this would be like a very harsh mitigation scenario where we actually meet the Paris goals. In that situation, a once per 100-year flooding event is becoming basically a once per year event, right? So we're saying this extreme sea level of 2 meters goes from once per 100 years to once per year, even if we like meet all of the climate goals. And so that's a very clear, direct example of climate change impact that's very tangible and needs something, needs some type of adaptation to deal with, increased seawalls, increased levees, something to deal with. And it's like very clear that that's directly attributable to global warming. This is another one of those historical trajectories of these things. So for observations from 1921 to 2017 of the number of days with high tide flooding across the US. And again, so this is something that's clear. It's not like the tropical cyclones where it's like, it's not really increasing. It kind of depends on how you slice and dice the data. It's like, no, with sea level, you see this clear upward trend, and it's also just directly attributable to global warming and climate change.